Good afternoon. I think I'm alone here. I'm gonna wait for a few of you. For those listening, today we have reserved time to try the binomial problems at the end of this unit, or this section of the unit. I'm gonna do several problems, and depending what kind of questions you have, I'm going to answer the questions and then possibly move on to the next part of this unit. Oh, computer's making a lot of noise. The streaming is okay, well, find this place in your notes. This is page number 5. Make it a little bigger. Now you can work on these problems, and also I mentioned the homework problems. The homework problems that are posted in the Moodle on the Moodle page. I'm just verifying that they're there. So if you're now we're in Unit 5, and under Unit 5 binomial, I have the lecture notes, I have the homework, and then the homework solution. So the answers are all worked out there. But if you want an explanation, let me know, and I can step through an explanation for you. Okay. All right, so let's see. If a fair die is rolled 6 times, the probability of obtaining exactly 1/5 is... All right, so what we have to do here, first of all, I've prepared these so you know in advance that they're all binomial problems. But if you can, develop a systematic approach that will help verify that it's binomial, and then it'll help you solve it. So what you need are these elements, x, n, p, and k. X is the number of successes. So if you can identify what the success is, if you can identify what the success is, then you're on your way. That's it, number. So what's a success? What am I looking for? What am I doing? What am I looking for? What am I doing? I'm going to roll a fair die. That just means that it's each side has the same chance of occurring. A fair die is rolled 6 times, and then must be 6. So I'm going to repeat the same thing 6 times. And what I'm going to look for is I'm going to look for the 5 turning up. Okay, a 5 will turn up. It might turn up on the first roll, or it might not. It might turn up on the second roll, or it might not. It might not turn up on the third. It might not. What I'm interested in, out of the total 6 tosses, how many times, well, in this case, what I'm interested in after 6 tosses, what's the chance of getting exactly 1/5? So the possible outcomes are erase this. I don't want to erase that. Well, let me write it again because I want to write this as x could be 0, 1, 2, 3, 4, 5, or 6 successes. N is 6 attempts. P is the probability of success. And I'm going to write it out here, where success is seeing a 5. I think I'm hearing hearing the wind. All right, so X and P, and then, well, what's the probability of that? What's the probability of seeing a 5 on any given roll? It's always the same, and it's always 1 out of 6. Okay, it's always going to be 1 out of 6. So the last element I'm interested in is K, the special K. Which of these possible outcomes, 0 successes, 1 success, 2 success, 3 success, up to 6 success, which of those corresponds to what I'm interested in? Exactly 1, 5 means I'm interested in just special K, that I'm just interested in K being 1. So I want to solve this just for one of these. So using the formula, I'm going to use the space here to apply the formula. So probability x equals 1 is equal to 6 choose 1. Okay, so this is the number of ways of seeing 1 success out of 6, and then I multiply that by the probability of a success to the number of successes, in this case just 1, and then by the probability of a failure to the number of failures. Well, if there's 6 tries with 1 failure, 1 success, that means there has to be 5 failures. Okay, so we check this plus this must be 6, and this plus this must be 1. So everything's correct. Now punching that into my calculator, remember 6 choose 1 is always going to give me back 6. It's going to always give me, so n choose 1 is always n. So I know the answer to that just to simplify things. Sorry, that will be 6. And then this is 1 out of 6. And then this is 5, 6 to the power of 5. Making it bigger always helps. Okay, so you know how to punch this into your calculator. You can further simplify. These will cancel. So all you're going to put in your calculator is 5 divided by 6, and then to the power of 5. And you will get the answer. I'm just going to punch it in to verify. I think I already know it, but So it's going to be 0.44, well, the larger I make it, the less sensitive it is. 4019, or 40%. Okay, so that is, oh my goodness, that's the answer. So what did we find out? We found that if we roll a die 6 times, the chance of getting exactly 1 5 out of all the different possibilities is 40%. That's pretty high, actually. 40% chance. Okay, so the answers, like I say, the answers are here. But I think it's important to understand what you're doing as opposed to just applying the formula, all right? So if you need to review the video from yesterday, but this serves as a review as well. Okay, let's do the second one. I have to erase this to do that. Gotta take it out of the way. Okay, next problem. The probability of observing no fewer than 2 heads in 4 tosses of a coin. Now we did this before, the tossing 4 coins, and we know the probability distribution, but let's use this opportunity to derive the answer using this method, okay, using the binomial formula. Before we did it by listing the possible outcomes, identifying what the probability of each one was, and multiplying by the total number of ways you could see the arrangements of whatever we were looking for. In this case, X, the number of successes in n tries, is going to be the number of successes, or the number of heads in 4 tosses. So we could get no heads, 1 head, 2 heads, 3 heads, or 4 heads. N is 4. P is the probability of a head on each toss. Well, each time I have 2 possible outcomes, a head or a tail. So this is 0.5. X and P, and then K. What am I interested in? In other words, which one of these am I being asked about? You're being asked about no fewer than 2 heads. Aha, so that's not just one of these. I have to actually calculate a few. No fewer than 2 means two, 3, or 4. So what you must do is you must calculate the probability that K is 2, the probability that K is 3, and the probability that K is 4, and you need to add those together, right? Another way you could do this is calculate the probability, the other ones, the other 2, and subtract the sum of the probabilities from 1 to find these as a group. But let's do it this way, if you're still trying to learn this. So I need to set up the formula for K equals 2, K equals 3, and K equals 4. So the formula is Okay, probability x equals 0, 2, is 4 possibilities, the number of ways of seeing 2 successes out of 4, times the probability of success, which is 0.5, to the number of successes, which is 2, times the probability of a failure, which is 0.5, to the number of failures, which is 2. All right, so just double checking. Together, these sum to 1, and together, these sum to 4. Then you have to plug that in your calculator to get the answer. So let me write them all out, and then we'll punch them in. So x equals 3. So that means I need all the possible arrangements of 3 heads. So how many ways of there of seeing 3 heads out of 4? So you're going to get a head, and a tail, and the head, a tail, a head. So all those different combinations. And then this is for 3 heads and 1 failure. So that's a different number. We have to calculate it. Okay, so this is a different number than this one, but you see the pattern. Now for x equals 4, this is 4 choose 4. Remember, it's not a fraction and it's not a matrix. It's a symbol for 4 choose 4. The number of ways of seeing 4 things arranged out of 4. And then this is 0.5, the probability of success. There's 4 successes. And then 0.5, the probability of failure. There's no failures if 4 successes. So those are what we're going to use compute on with our calculator. Let's make those smaller. So with the calculator now, this is going to be 4 second function NCR2, which gives you 4 choose 2. We did this before, so you should know what it is. 4 second functions NCR2. That's 6. So this is 6. And then, so it's going to be 6 times 0.5 squared times 0.5 squared, which just works out to be 0.5 to the 4. So it's going to be 0.5 y to the x 4 times 6. So this should look familiar. This is 0.375. Then the next 4 choose 3. Now we know the number of ways of seeing 3 things arranged out of 4 possibilities. When it's just one less, when this is just one less than the n, it's always the n, right? There's going to be only 4 ways to arrange 3 successes out of 4. So this one is 4. And then you're going to multiply it by 0.5 to the power of 4. And then the last one, this one is always going to be 1. It's only one way to see 4 successes out of 4. And I talked about this yesterday, just to remind you, this is 4 spots. How many ways are there of arranging 4 successes? Well, there's only 1. So that's why it's 1. And I multiply it by 0.5 to the 4. And you should recognize that number is 0.0625. Alright, so these should be familiar if you remember from working on this in the probability unit. And my answer is just summing these together. So I'm going to add those to find the probability that more than, how was it termed? It's a little bit frozen. Hello. My screen is frozen. Okay. So when I sum all those together for no fewer than 2, so it's either 2, 3, or 4, I add those together and I get 0.6875. So 69% chance. All right, so that's nicely presented in the notes if you go forward a couple of pages. But that's my explanation. All right, let's look at the next one. Suppose that 60% of a herd of cattle is infected with a particular disease. So X is the random variable representing the number of cattle that are infected. In a sample of 5, let Y denote the number of cattle that are not infected. What is the distribution of Y? Okay, well, since I can identify X, let's do that. Let's continue the same systematic approach that we just used. So X, N, P, and I don't know that there's a K here. No, just X, N, and P for now. So X, so let's start with the N. Usually I start with the N. So what are we repeatedly doing? We're repeatedly checking to see if a cow, or yeah, I guess a cow, is infected or not. In particular, I want Y to denote the number of cattle not infected. So that's what I want. That's my success, not infected, which makes sense. And X could be, oh, it's not even X, is it? I want to use Y. It's for Y. Just to be clear. Same idea as before, but it's called Y. So Y could be, sorry, I'm going to check how many times. I'm going to check a sample of 5. So that's going to be what I'm going to repeat 5 times. So there could be 0, 1, 2, 3. Let me go back. Let me say this is 5. Let me make this bigger. Those are the possible outcomes for Y. And And P is the probability of the cattle not being infected. Well, if the chance of being infected is 60%, that means the chance of not being infected is 1 minus 60%, so that must be 40%, or 0.4, right? So that means that the answer is that it is binomial, because I was able to identify N and P, and I am counting to look for the number of something, and success is, in this case, non-infected cattle. This binomial with an N of 5 and a P of 0.4, so the answer is B in this case. Okay, that's my answer. Okay, let's try the next one. Maybe we can do the whole set of problems before the hour is up. So if you want to stop the video and go back and review, you can do that and pick up with number 4. Number 4. An African hospital is treating patients who have Lassa fever. 70% of patients with this disease die, and each patient lives or dies independently of other patients. That's very important. Sounds like a binomial. Let's see. Let's see if we can set up X, N, P, and K to solve the problem. What are we looking for, and how many times are we looking? We are looking to see if someone, well, the last sentence is going to help us. The probability that 6 patients or less die, the way that that's phrased, what I'm going to be looking at when I look at the 7 patients, there's 7 patients, so I'm going to repeatedly look. I'm going to look at each one, and what I'm interested in is if they're alive or not. So the success is going to be defined as, unfortunately, I'm going to define success as death. Okay, so it sounds strange, but that's what I'm looking for, if they're dead or not. So X can be no one died, which would be great. 1 person died, 2 people died, 3 people died, 4 people died, 5, 6, or 7 people died. The P, the chance of dying, well, we were told that 70% of patients with the disease die. So that is the chance of dying. All right, so there we have it. What am I interested in, though, for the question overall our sample? What I'm interested in, 6 patients or less die. 6 patients or less would be all these possible outcomes. So like in the one before, I would have to sum the probability that X is 0 to the probability that X is 1 to the probability that only 2 people die to the sum to the probability that 3 people die, etc., all the way to 6. Now that's going to take a much longer time than if I simply did something else. What's the thing I could do? Well, if I calculate the probability that everyone dies, and I subtract that probability from 1, I would have calculated any of these possibilities happening. Okay, so what I'm going to do is I'm going to use, let me write it here so it's clear. that I need to add 0, 1, 2, 3, 4, 5, and 6, or I want to use 1 minus probability. Oh, you can't see that. I'm going to calculate 1 minus probability x equals 7. That's going to be my approach. I know this is binomial because I've identified all the parameters. And so I set it up. Don't forget about the 1 minus. I'm going to raise this up. And this is what I want to calculate. So it's going to be 1 minus, put a big bracket. So the number of ways of seeing 7 out of 7. The chance of death is 0.7. This is a horrible disease. The probability is 0.7, and I'm looking at 7 people dying. Survival, 1 minus. So the only other outcome, either they died or they survived. The chance of survival is 30%, but I'm looking at the probability of none surviving, all dying. So what I want to compute is this. This is the outcome, x equals 7. That's the probability. When I punch that in the calculator, I can simplify. I mean, you don't have to simplify, but it's nice. I always know that's going to be 1 because there's only one way of seeing 7 successes out of 7. Remembering the example. How many ways are there of seeing S's, you know? There's only one way of seeing 7 S's. And then this is going to be 1 as well, because anything raised to the power of 0 is 1. So all I really have to do is take 0.7 to the power of 7, and if you still don't know how to do that, that's going to be 0.7 y to the x 7 equals. Okay, that'll give you that value. Unless you have a different calculator. Most calculators that I recommended will be done this way. Y to the x 7. So this is going to be then 1 minus 0.082353. So all I want you to keep when you solve these problems, I just want you to keep 4 decimal places. That's all you need. Okay? I'm very happy with that. Just make sure you round them. Did I round? I didn't round. So this needs to be a 4. Fix that. Make this a 4. A 4. Have to round that. And so that makes it 1 minus 8%, 8 and some. So you could put a negative in front of it and add it to 1. That's how I do it on my calculator. So this works out to be 0.9176 or 92%. Okay, so it's a high chance that, it's 92% chance that as many as 6 people die. Well, let's say it properly. That not everybody dies. But I don't know if that's the right way to say it. That 0 or 1 or 2 or 3. So the way it was phrased was that less than 7, what does it say? Oh, 6 or less die. 6 or less die, 92% chance. It's a lot. All right. So that's that page. I finished that page. Let's save this. Did something happen? I got booted out. Okay. So now let's go to Okay, let's go to the next. Remembering everything we did. Right. Did I skip all this? I don't believe I skipped all this. No. Where are my exercises? Okay. All right, so here we are. Okay, we have a SARS problem. A SARS problem. This is probably the most challenging one, but once you see it, hopefully you can replicate it. There are 4 patients with SARS in a Toronto hospital who are monitored by 2 staff members. Suppose the probability of a patient requiring emergency attention by a staff member is 0.3. Okay, so the chance that someone needs attention by emergency staff is 30%. Assume the patients behave independently. So that's important. So that means that if someone needs attention, it doesn't affect if another person needs attention. Okay, these individuals are independent in their manifestation of illness. What is the probability at any one time that there will not be sufficient staff? Okay, so this is a little to unravel here what's going on. You can pause the video and read it again. See if you can identify X and PK and come back. Or just stick with me and I'll show you. So X, N, P, K. What are we repeatedly doing? We're repeatedly, well, let's start back a step further back. What is a success? What are we looking for? What are we looking for? We're looking for, so the last sentence always tells you what it is that you're interested in. What is the probability at any one time that there will not be sufficient staff? So you need to translate this problem into the elements of the problem. Not be sufficient staff there not being sufficient staff is the same as what? Well, if I was to define the success as needing attention, so let's try that. I'm going to define success as needing attention. Okay, so success equals needs attention, and there are how many people? 4. So there's 4 people that potentially need attention, and each time we're going to check either none, 1, 2, 3, or 4 need attention. The chance of needing attention is 30%. So the way I figured out that the way I figured out the success was working with the information I was given about the probability. Okay, I have to actually start from there. So it was actually this sentence that tipped me off. So the patient requiring emergency attention by the staff is 30%. That's the only figure I was given. So that's how I have to frame the problem. or my response to the problem. So success is needing attention, which is a sad thing, but that's what we're looking at. Either none, 1, 2, 3, or 4 people need attention, and is therefore 4. The chance of needing attention was given as 30%. And the K that we're interested in is going to be that which answers will not be sufficient staff. So in what instance will there not be sufficient staff? Well, there's only 2 staff members. So this is the other critical piece of information. There's only 2 staff members. So because there's only 2 staff members, the problem of not having sufficient staff will only happen if 3 or 4 people need attention. Okay, so this is what I mean about unraveling. We frame it the way the data has been given, or the parameters, the information we're given, and then answer the question with the frame you have. Okay, so the question was, will not be sufficient staff, and we see that the way we've drawn it up, if there are 3 or 4 people that need attention, there's not going to be sufficient staff. So what I'm going to calculate is the K for 3 and 4, and I'm going to sum them together. And that's how I solve this. Let's do it. Okay, so as I mentioned, print out the notes or have them in front of you when you work on this and review, so that when I cover the question, you're not lost. So I need to use the formula for x equals 3 and for x equals 4, and then I have to sum those. So x equals 3, out of 4 patients, 3 people needing attention, the probability of needing attention is 30%. 3 of them need attention. The probability of not needing attention is 70%, which is great, and only 1 person would need that. So remembering that's the probability of a success to the number of successes. This is the probability of failure to the number of failures. Next, it's going to be 4 choose 4, 0.3 to the 4, and 0.7 to the 0. And we move that over. That's a 0. Okay, that's a 0.7. So we can simplify, or you can punch this right into your calculator. Simplifying works for me best. So this is going to be 4, because the number of ways of seeing 3 out of 4, or n minus 1 out of n, it's always going to be the n. We talked about this yesterday. This is going to be just as it is, 0.3 to the 3 and 0.7 to the 1. If I punch that into my calculator, so you should use brackets if you're going to try and get my answers. 0.3y to the x3 times 0.7 times 4. So this is going to be 0.0 0.756, and the other one, this is going to be 1, and this is going to be 1. So all I'm using is 0.3 to the power of 4. So this is 0.0081. So I sum those. and I get 0.0837. And that's that. And let me double check. That's the answer. Okay, so I wrote it up nice and neat here. This is what we just did, computed, and then I wrote it like this: x greater than 3 or 3. It should be greater than or equal to 3, actually. And then the answer is 8.37%. So I got it right. Okay, maybe one more. No questions? No questions. The probability that a certain machine will produce a defective item is 25%. If a random sample of 6 items is taken from the output of this machine, what is the probability that there will be 5 or more defective in the sample? So, what am I looking for? I'm going to look at the output of the machine, and I'm going to see if items are defective. So success is defect. Okay, so let me write that by just circling here. This is success. Okay, that's what it would be, our success. All right, so let's see. Can we list it as a binomial problem? Can we identify x and p and k? X, N, P, K. What are we repeatedly doing? We're checking a machine. We're going to check a sample of 6, and because it's a sample, we're assuming, well, that the chance of seeing 1 is defective. Well, so let's say that differently. The chance of having a defective item did not get affected by having previously seen a defective item. That would be independent, which is not necessarily true, but we're going to assume that in order to apply the binomial here. Not necessarily true, because if the machine is operating incorrectly and one item is defective, maybe the next few items have a greater chance of being defective. Okay, but in this case, we're going to assume that the defects are independent. So we can apply the binomial. The probability of seeing a defect is 25%. And I want the probability there will be 5 or more. So X could be 1 defective item, 2 defective items. Sorry, 0. I have to always start with 0. Don't forget 0. 0 is very important. Okay, no defective items, 1 defective item, 2, 3, 4, 5, or all 6. But this question, I want to find the probability that there will be 5 or more defective. So I just want to calculate 5 or more, so 5 or 6. So that will be my K. So I need to find the probability when K equals 5 and add it to the probability that K equals 6. Let's do that over here. X equals 5. Then we would say the number of ways of seeing 5 successes out of 6. I want all those arrangements. And there's only actually, well, there's going to be 6 ways of seeing that. And then I'm going to multiply that to the probability of defect for how many defects I'm going to see. In this case, it's 5. And then I'm going to multiply that by the probability of failure. And the number of failures I'm going to see, well, if 5 are defects, then 1 will not be defected. Then I'm going to do the same for 6 defects. So all defective. 6 choose 6. That's the number of ways of seeing 6 successes, or 6 defects out of 6. The probability of defect is 0.25. And there's 6 of those. And then there's none that are good. Again, remember that these sum to 1. And these must sum to the total n trials, or n in our sample, 6 in this case. So to simplify a bit, 6 choose 5 will be 6, right? Because the number of ways of seeing 5 successes out of 6, 1, 2, 3, 4, 5, 6. So successes, 5 successes would look like this. And now, how many different arrangements of 5 successes are there? Well, we can just imagine shuffling F through the list. So F can go here, F could go here, F could go here, 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 or here. That's 6 possible ways. And then basically multiply that through. And then the same thing below, that will reduce, this will reduce to 6 choose 6. It's always 1. There's only one way of seeing 6 successes. There's only one way to see this. Okay, so as I said yesterday, n choose n will always be 1, and n choose n minus 1 will always be n. As well, n choose 1 will always be n. Okay, so then here, this will also be 1 because it's a power of 0. So that's easier to punch in. So let's get the results. Punching it in. This one is 0. Very small, 0.0044. I'm rounding to 4 decimals. And I'm going to start with 0.25 to the power 5 to do that, and then multiply by 0.75, and then multiply by 6. Just checking I got it right. Okay, yes, that's correct. And then I'm going to take 0.25 to the power 6, and that's a very small number. That's going to be 0.0002. And when I add those together, the total answer is 0.0046, and that's my final answer. Because I have to sum those to get the answer. So the chance of 5 or 6 defective items is small, and it's 0.46%. So that answer is E. All right. Okay, well, maybe I can go early. You let me go early if you have no questions. The rest of the problems are worked out, so you can review them. In the homework exercises, there are several problems. Similarly, I have the problems worked out for you. So try and attempt them on your own and then look at the answers. I don't recommend just the false sense of security where you have the answers and you think because that you're going to be fine. Please take the time and work through these. Keep up. On Thursday, we're going to have a quiz. What I'm going to do tomorrow is begin, like I'll leave these for you to work on. These are for you to practice. And I will begin here on page 16. All right? So if you don't have any questions, I'm going to let you have a good night. Bye.